Hello, everybody out there in Math 150 land. We're going to be looking at section 6.4 this evening, and that's going to be trigonometric identity. So here's the idea behind a trigonometric identity. An identity is something that is always true. You could say that 3 plus 7 equals 10 is an identity. And what that means is 3 plus 7 has another name. It has the name 10. So you could use them interchangeably anytime you want. The identities that you're going to be responsible for as we look at this next section are the ones listed on the screen here. We talked in the last section about the Pythagorean identities, and that says sine squared plus cosine squared equals 1. Again, totally interchangeable. If you wanted to say sine squared plus cosine squared, you could replace that with 1 anywhere you saw that. Okay. We showed that by dividing this first identity by different things, we can actually derive these next two. So we're going to get tangent squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. And what you want to remember about this is that every trig function has a squared identity. So if you're ever doing a problem and you see a trig function being squared, you need to say, hey, is the identity going to be useful? Maybe you can manipulate it using that identity. So the next identities, which we haven't talked about directly, but we've mentioned earlier in the course, we've talked about even and odd functions. And remember, an odd function is a function such that if you plug negative x into the function, it becomes negative f of x. So in other words, the negative just jumps out to the front. These are symmetric around the origin, and we know by looking at our graphs that we've done that there are 4 of these odd functions. When you're talking about trigonometry, I have 3 of them listed here. Let me add that fourth one. All of these are odd because they are symmetric around the origin. So the last one I'm missing is cotangent, and that's going to be equal to negative cotangent x. So sine, cosecant, tangent, and cotangent are all odd functions. They're all symmetric around the origin. So you can pull that negative out from the angle and bring it to the front. The 2 even functions we have in the world of trigonometry are cosine and secant, and that should make sense because those are reciprocal functions. So then you plug in into an even function. When you plug a negative into an even function, the negative just disappears. And that's what's going on here. These are symmetric to the y-axis. One other set of identities that I want to remind you of are the reciprocal identities. I actually refer to these as just the trigonometric definitions, but this is how you can rewrite all the trig functions. We've listed these before. Sine x is the same as 1 over cosecant. Likewise, cosecant will be the same as 1 over sine. Cosine is the same as 1 over secant, and secant will be the same as 1 over cosine. So these are reciprocal pairs. And then, of course, tangent is the same as 1 over cotangent, and cotangent will be the reciprocal of 1 over tangent. And just one added bonus, as long as we're listing all of these here, let's just look at one more set. You should also know that tangent x can be rewritten in terms of sine and cosine, and that's sine over cosine. And since cotangent is the reciprocal, that will be cosine x over sine x. This is all the identities and the definitions that you're going to want to be familiar with. We're going to make use of these. We're going to do several short videos on this section, getting you guys to look at different ways you can solve and work with identities. So today we're going to look at these 3 examples. We're going to look at just simplifying these 3 examples, okay? So we're going to start off with the first one. We've got tangent over secant. Well, one thing that you might want to think about is you might want to think about how tangent is really sine over cosine, because for a lot of us, it's much simpler just to go back to sines and cosines when we think about these. And then secant is equal to 1 over cosine. So one way of doing this is making a very large complicated fraction, because the tangent part is going to end up being replaced by the sine x over the cosine x. So that part goes right in the top, so the yellow matches to the yellow. And then the secant x can be replaced by 1 over cosine x. So that's our reciprocal identity. So the green matches with the green. And from there, what we can do is we can divide fractions. We're going to take the numerator. So whenever we have a complex fraction, what we want to do is we want to multiply that entire numerator, which is sine over cosine, by the reciprocal of the entire denominator. Well, the denominator is 1 over cosine x. So the reciprocal of that will be cosine x. So when you multiply these together, you end up with just sine x. Okay. One thing I do all the time with my students, and I'm going to show this to you guys, and I hope this is going to resonate. I'm going to give myself a little more space here, so I apologize. Just give me a second. Let's move that down a little bit. Okay. I like to do a little shortcut on this and see if this makes sense to you. What I like to do is I like to play this game where I say a tangent in the top. Okay. Anytime you have a tangent in the top, a tangent in the top is the same as a sine on the top and a cosine on the bottom. So I like to write this not as sine x over cosine x, but instead what I like to do is I like to do it this way. I like to make it so they're separate fractions. Okay. They're separate fractions. Now, if you imagine these being multiplied, this is still sine over cosine, this is still tangent. This still matches back to the tangent that we have on the top. All of this is that tangent on the top. So now what I like to say is a secant. Well, typically a secant, when it's on the top, when it's in the numerator, that gives you a cosine in the denominator. So a secant on the top is the same as a cosine on the bottom. Well, this is the reverse. This is a secant on the bottom. So that's really going to give us a cosine on the top. So what I like to do here is I like to just put another fraction. I like to put a cosine on the top. And then I can say that this matches to the secant part. So this spread out expression is the same as this fraction. Tangent on the top is sine over cosine. I see it here. Secant on the bottom puts a cosine on the top. It's right there. So from here, I can just look at this. I can be like, those cosines cancel. There you go. I've got sine x. So using the reciprocal identities that way can be really helpful. You might see some more examples of that as we go along. So let's take a look at this next one here. Let's go and take this guy. Let's copy that. And let's take a look at this one. So here we go. This one, what we want to do is we want to simplify this expression. Now, I'm going to warn you, the first thing I thought of when I saw this were those Pythagorean identities because I saw these squares. And I always like to try to think about the Pythagorean identities. But since we're just trying to simplify this, another thing you can think about is we've got degree twos. And anytime you've got a degree two, you want to think about factoring. And the bottom lends itself very nicely to factoring because we've got a greatest common factor of cosine. So what we're going to do is we're going to take out that greatest common factor of cosine on the bottom. So out comes cosine theta. We're going to be left with cosine theta minus 1. If we distribute that back in, there's our cosine squared. There's our minus cosine, so we're in good shape. And now on the top, I think in the last section, I talked to you guys about treating these trig functions like variables. If this were x squared plus 1, I hope you would do a difference of squares. I hope you'd say x minus 1 and x plus 1. Well, if it's cosine squared minus 1, we're going to use that exact same idea. We're going to treat this as a difference of squares, and we're going to get cosine theta minus 1, and we're going to get cosine theta plus 1. And when we do this, what we're going to notice is that we've got common factors right here and here. Well, anytime you've got a common factor in the numerator and the denominator, you can cancel those out. So now what we're going to be left with is cosine theta plus 1 over cosine theta. And there's nothing wrong with that answer. You could leave it like that. But I want to show you another little algebraic maneuver we'll be using a lot of the time here. When I look at this, I see a fraction and I see addition. Whenever I think about a fraction with addition, that always gets me thinking about common denominators. But you might say, hey, we've already got one fraction. Well, what I want to do is I want to say, where did this fraction come from? It was really two fractions that were being added together with a common denominator of cosine. That's what's going on here. So I'm going to break apart this fraction by using its common denominator. That's going to give me a cosine theta on the top of the first one. It's going to give me a 1 on top of the second one. If we continue with this, what we're going to find out is we've got common factors on the top and bottom again. So that's going to turn into 1. And now I've got plus 1 over cosine theta, which is fine. But again, if I want to use a reciprocal identity here, 1 over cosine is equal to secant theta. So I'm going to end up with 1 plus secant theta in this problem. And a lot of people say that is the simplest way you could do this. So you're going to see us manipulating a lot of trigonometric problems during this section. Let's take a look at this one little more. Let's take a look at this last one. Let me copy this one and bring it down. So on this last one, what we've got is we just want to simplify this product, okay? So we could just start off by distributing this. There's nothing wrong with that idea. That would give us right here cosine x tangent x plus cosine x cotangent x. But now what I really want to do is I want to look at this as two parts. I want to look at this as my first term, and then I want to look at it as my second term, and I want to think about, can I simplify anything here? Well, I'm going to warn you, I'm very, very partial to cosines and sines. I like writing things using cosine and sine. Because of that, I'm going to keep that cosine exactly the way it is, but that tangent, I'm going to turn that guy into his cosine and sine counterpart, and that's sine x over cosine x. Likewise, I'm going to keep that cosine exactly the way it is, but that cotangent x, I'm going to turn into its cosine and sine counterpart. That's going to be cosine x over sine x. Well, we're going to see some nice things starting to happen here. We're going to have a factor of cosine on the top and a cosine on the bottom. That's going to leave us with sine x as that first term. And now in the second term, we're going to get cosine times cosine gives us our cosine squared, and it's all over sine x. From here, what I'm going to think about doing is I'm going to think about adding these two fractions. So I want a common denominator for both of them. The denominator for sine is 1. That's pretty agreeable with any denominator. So the sine x from the second denominator is going to go into the common denominator, and there's already a 1 there. That's fine. So now we're going to ask, how do I get from this denominator to this denominator? What do I multiply 1 by to get me to sine? And the way we're going to do that is we are going to multiply the bottom by sine x, and we're going to multiply the top by sine x. So when we do that, we're going to get that sine x over, I'm sorry, sine x times sine x on the top. That's going to get us sine squared. On the bottom, we're going to get sine times 1, and that's what we have in that denominator, so we're fine. We're going to add to that the fraction with a denominator of sine x already, so I don't have to do anything to this guy. He's automatically sine x, so I don't have to do anything at the top. That's going to give me cosine squared on top. Well, from here, you got to think about squared identities. This is the Pythagorean identity. Sine squared plus cosine squared is equal to 1. So where I have this sine squared plus cosine squared, I'm not going to have it for long. That's got the same value as 1. So now I've got 1 over sine x. Well, that's a reciprocal function. That's the reciprocal of cosecant. Cosecant is 1 over sine x. Okay, 1 over sine x is cosecant. So this is going to give me cosecant x, and that's the final simplified answer. I'm going to make several videos this afternoon showing you guys how to simplify these expressions. We're going to be looking at identities in this section. Let me know if you have any questions. There'll be another video coming shortly.